We have started recording. Remember. Okay, so let's start. I'm a bit sick, so you'll be hearing me coughing and sneezing a lot, so not to worry. Okay, let's start. מי שברך אבותינו ואמותינו אברהם, יצחק ויעקב, שרה, רבקה, רחל ולאה. הוא יברך וירפא את כל חולינו וביניהם. הזקוקים לרפואה שלמה, בעבור שאנחנו מתפללים להחלמתם. בשכר זה הקדוש ברוך הוא ימלא רחמים עליהם, להחלימם ולרפואתם, ולהחזיקם ולהחיותם. וישלח להם מאיר רפואה שלמה מן השמיים עם כל חולי ישראל. רפואת הנפש ורפואת הגוף, השתה בעגלה ובזמן קריב, ונאמר אמן. יופי.
Amen.
Oh, so you guys can see, yes. Okay, loaded. Okay, what are we going to do today? Oh, wrong course. It's not a Tanakh course, nachon? Which course are we in? Data structure? Oh, yeah, data structures. What's that have to do with data structures? Okay. Take a review. We're going to make some order in all our sorting methods, decision trees, lower bound, stable. Wow, look at this. A lot of things. Some things take 2 minutes, some things take 10 minutes, 15 minutes. And then we'll talk about linear sorts. And we'll be seeing today 2 of the 3 sorts that we learned in this course. This is what we're going to be doing. So, like this. There's a pasuk in Kohelet that says, Lev chacham liyamino v'lev ksi l'shmolo. The smart guy, heart, he looks to the right, and the foolish guy looks to the left. There's a lot of different explanations if you look at the different mefarsim, but one that I heard, I never saw it actually written, I should look it up. I heard the name of the Gaon Mevilna that said like this: what's the Lev Chacham Yamino? When you have a book in Hebrew, when you open it, all that you've read and studied is on the right-hand side. That's the wise guy. That's the guy who's wise. It's Chacham. The foolish guy looks to the left and says, oh, I got so much to do, forget it. And just closes the book. Or there's so much more to do. No, that's not for me. What I want to do now is let's look to the yamin. Let's look to the right. Let's see what we've done so far. And this way, also to answer the question that was before we started recording. So I'm taking you back to our first lesson. When I presented to you the course, and there were a lot of different things here, different names and different topics that you had no clue about. It could be that you still have no clue about it, don't know, but okay, let's assume yes. So the first topic was, we talked about, here's an algorithm, how do you analyze it? We talked about the runtime, the complexity of the runtime, and how to look at the order of magnitude, the complexity, and then we saw some notation, specifically big O, theta, and omega, which help us define different groupings of algorithms, the runtime of these, the runtime complexity of these algorithms. That was the first topic. Then we started actual data structures. We started looking, now these are the key, not the main things, but most of the things. Obviously there's a lot of other things inside, but we talked about data structures, arrays, like data structure, a linked list, a single linked list, a double linked list. What's it, rounded list? A rounded list, that's missing this. A sparse matrix, we even saw the concept of a sparse matrix, and okay, how can we implement it? We saw a stack. Q. We talked about LIFO and FIFO. We talked about a lot of different topics in that chapter, let's call it. Then we took a break. And we went and took a break and revisited recursion. For some of you, it still is trauma. Recursion, some of you, it's okay. You're managing with the recursion. We reviewed stuff that you did in the introduction to CompSci course, and we started looking a bit more deeper into the recursion. We looked at merge sort. We looked at merge sort as a algorithm which is recursive, which you saw in the first semester, but we drilled down a bit on it. And you saw here even another one called quicksort, another recursive sorting method. All that dealing with the recursion was towards dealing with trees. Trees, which is a recursive, how we define a binary tree, it's a recursive definition. And basically we're doing a lot of things recursively. Not everything. Transversals, we saw that you can do a transversal according to levels, but there's also depth transversals, which is totally recursive. And a lot of the algorithms we write with trees are recursive functions. So we started seeing binary trees and how all the different definitions, what's the internal node, what's the leaf, the height. Height's very important. The height and all these different things. After that, we saw a special type of tree, which is called a binary search tree. It's a binary tree, but it also has extra things, left to the right, whatever. Then we saw another type of tree, balanced trees, another groupings of trees. We could see what's a balanced tree, where we want to keep some type of balance. We don't want one side to be lopsided. We don't want the tree to fall over. We want it to be like that. Then we saw a specific type of BST called the AVL, an AVL tree. It's a BST to begin with, lecatchila. Over and above that, it's balanced. And then we saw something else, another type of tree, which is called a heap, which is totally different. It's not a BST, nothing to do with it. You have heaps. And we saw heaps. After heaps, we saw a priority queue. A priority queue is another data structure, which we can use a heap to implement it. With that, we saw here other sorting methods. We saw how to do a binary sort using an AVL. We saw a heap sort. Again, more topics there. We saw heapify. We saw the whole idea of doing rotations. Right? There's a lot of stuff inside this big chapter, but these are the main points. To do AVLs, we learned rotations, heaps, we learned heapify. That's what we've done. I know it's on the left-hand side, not on the right-hand side, but it didn't work out. What's still to finish? One more topic, just more sortings, which is called linear sorting, which we'll deal with today. And today we'll talk in general, and then we'll talk specifically about count sort and radix sort. And Bezat Hashem, next week, we're going to say chazak, chazak, v'nit chazek, or hadron alecha, everybody according to what you're doing. And we're going to be finishing all the material. Like I promised, we'll be finishing lefachot, at least one, I had said 1 week. It's going to be a bit more than 1 week earlier than the end of the semester. And that's deliberate, because there is another chapter further down that you can't see, which is preparing you guys for the exam, which is not less important than learning all the different material. So basically what's the plan is the following. I didn't send you out to the Hebrew speakers and to my girls group. I sent a whole calendar, but because they study more than 1 day a week. But here we only have Thursdays, so it's just easier. So this week we're going to be seeing what we're doing today. Next week we'll finish off the bucket sort. We'll be doing some more exercises. We'll do actually exercises, recitation, let's call it even, on these sorting methods until we understand it more fully. And then already next week, we'll be starting to talk about the exam, what it looks like. Hopefully by next Thursday, I'll know how it's constructed this year because of the Corona business. Yeah, today there was a whole big, sorry, and the lecturers in the course, the course coordinator was asking what's their opinion about making some changes. And once we know, obviously, I'll tell you all how's the exam how's it going to look this year. Hopefully, it won't be very different, if at all. It will just be better from the student's point of view than previous exams. We're talking about it, how to get ready for it. And what we're going to be doing is starting to go through previous exams and solving it. I'll be sending you out sometimes beforehand for you to prepare things so you can see before class. Some things I want to do in real time so you can get the feeling of, okay, how much time does it take you to do? Sometimes you'll work levad, sometimes maybe in chavusas. And we'll be doing that already starting next week and the week after. This is week 10. We have 13 weeks, so 11 and 12 we'll do that. Week 13 is this very special week. That's basically, from our point of view, it's the end of the semester, because the semester finishes on the 30th, the Tuesday after that. That's our last Pigisha. We're going to have an event of finishing of the course. Now, I don't know exactly yet how it's going to work, because obviously things are very dynamic, what's going on with the corona. But there will be some type of event. It might even, hopefully, it might even be on campus. We can actually see each other. To finish off the course, just like we started seeing each other, at least to finish off. Again, I don't know all the details yet. I know what I want to do, but once we get closer, I can tell you what's going to happen. And I'll be giving out some candies to those, maybe to everybody. Okay, so that gives you an overview of what we've done and what we're going to be doing until the end of the semester. Questions until now, anybody?
Yes, previously you said that at the end of the semester there will be like answer sheets for all the homeworks.
Yes.
Will they be translated to English also?
Ooh. Wow, thank you. You just gave me extra work. Nachon, you're right. The course coordinator has already put up to question 6, up to number. No, sorry. Which questions? The answers to the homeworks or answers to the Targilei Kita? The difference, the class exercises.
No, the class exercises are already on the slides, no?
Yeah, the class exercises, I incorporate a lot of them into my slideshows.
Right.
A lot of the questions are built in to it.
Right. I was referring to the homeworks.
Of the homeworks, he hasn't put up answers to the homeworks.
No, but I recall you saying previously, like maybe a week or two ago, that at the end of the semester, they put up the answers. It could be they didn't yet.
No, it was the answers to the class exercises, not to the homeworks.
Oh.
Especially now, the homeworks, I don't see him doing that because people are getting all these extensions because of Corona, and it could be that you'll be able to hand it in, late, without penalties for a while. I don't see homeworks coming so quickly. I don't see it. Okay, but if there is, then they have to be translated. Okay, I wrote it down. Thank you.
Aren't most things, as far as answers, like, especially coding, I mean, maybe pseudocode not so, but like the language is not really, pseudocode is its own language. It's not really in English or Hebrew, is it?
Nachon, but pseudocode. But we only write in pseudocode in this course. We're not doing any C++ here.
Yeah, but I mean, if I saw it in Hebrew, maybe I'm wrong.
Yeah.
But I don't think it's really.
Yeah, it shouldn't be a problem, except for when there's explanations. When they're explaining what is the complexity of the algorithm, the explanation would be in Hebrew. Now, obviously, the pseudocode is in English. Right? It's not even in Hebrew, the pseudocode, right? It's English words, but you have the advantage of the Hebrew speakers. But you're correct. But okay, I'll see what we can do. Thank you for the idea. Anything else? No? Okay. Now we're going to do something a bit different. Yo, a bit different. What's that mean?
Can I ask a quick question?
Sure, please.
About the Chumash.
Yeah.
Right. So I got it from the library. It's a very thick book.
Yes, I know.
So can you have like some guidelines what to read?
Which chapters? Okay, I can try to make a reading list a bit. CLRS, Coleman thing, yeah? Reading. Okay. I just remind you, AVL is not in the book. It's an exercise there, right? Oh, sorry. But definitely, I'll try to prepare something. Okay. Anything else?
You said you talk about the homeworks?
Yes. Okay. In relation to the homeworks, kacha. Two things in relation to the homeworks. One, in the Hebrew versions, sometimes they find mistakes, and the course coordinator makes corrections. And not always does he remember to tell us, even for the Hebrew lectures, Kal V'chomer in English. Now, I always get the Targilim beforehand, and I translate, and sometimes I find mistakes, and he corrects them before he even puts it up in Hebrew. But there is one problem, because he takes a Word file. I have the Word file as well. But he puts it up as a PDF. And when a lot of times with the PDF, if there's a list of numbers, it gets reversed by mistake, and he doesn't always pick up on that. You can see where the period is, the full stop, at the end, and you can see that it just got reversed by mistake. Now, I have the original, a lot of times, the Word file, and I take it as the original. So basically, it's like this. You guys use the version you have in English. There are the Hebrew version, I think it was the stack question, with the pops. Yeah, with the pops. There was a whole thing there that was reversed. And basically, the answer is you can get it twice or something like that. But it didn't really check what you were supposed to check. That's not your problem. You did it. You wasted time even trying to figure out something which wasn't there. And you hand in as you are. Now, if you see in the Hebrew version it's a different list and you want to sort of practice yourself and to really understand it a bit better, then that's very good. It's another example. It's another exercise for you. But to hand in, you can hand in either according to the Hebrew version or the English version if there is a differential between them. Okay? Did you get an answer to?
Do we have to write which one we did so they know when they check?
No, you can. That would be just nice for the checker, but I'm sure he'll realize. I mean, he can see the numbers are totally different. And he knows that there's the problem of the difference between the Hebrew and English. That he knows about. He's aware of that. Yeah. In relation to handing in times, I'll just remind you, there are dates, right? I think this Motzei Shabbat is exercise 6. And then every Motzei Shabbat another one, until even after the semester. Exercise 10, there are 10 exercises. I'll talk about that in a minute. There are 10, and it's every Motzei Shabbat from now. Now, the boxes, the place where you can put it in, are still open afterwards. So you can hand it in late. You won't get penalized for it, that's for sure not. And because it's in red, the date, it says it's overdue, don't worry about that. Nobody's going to look at that. The only time when it's finished is when he actually closes and he won't be accepting anything at all. But definitely there's a due date and then there's a closing date of the actual teva, of the actual box. And he's changing the dates all the time of the last time things can be submitted. Don't count on it all the time, but definitely he does take that into consideration. In relation to the Targilim exercises, there are 10 exercises this year. Up to now, there's always been 9. I'll be talking next week. What is the 10th topic? Because theoretic is saying, okay, exercise homework 9 is about linear sorting. So it's linear. What's number 10 about? We'll be talking about that next week, and you'll see why it's super important. That's probably one of the most important exercises. I haven't really looked through the questions yet, but what I can see, it's exactly what I asked for. And definitely, but it's still 7 out of the 10, the best 7. Hand in all 10, and you take the best 7 marks. As you've got a letter, or maybe you didn't see it, I don't know if they put it out to the English speakers, every course coordinator has to, by the 4th of June, which is probably today, inform the academic secretariat if there's a change in the weight of the targilim, of the exercises. There is some talk now between the lecturers, maybe to up the value of the exercises from 10% of this course to maybe 15, even somebody said 20. The maximum you can put it up to is 20. And that obviously is just it's just for your own good. Because usually in the exercises, you get high marks. So instead of 10%, if it's 15 or 20%, that's just helps. So that's something that we'll know next week, exactly what is the weight of the exercises. Okay, did you get a full answer about the homeworks? Yes?
Yep.
Good. All right, so now we're going to do something different. I'm assuming that everybody here has, obviously, a computer or a telephone. And what we're going to do is the following. We're going to sum up a bit in a bit different way. It's important for me and also for you to see where you're holding in the course according to different topics. Because I want to plan the next 2 weeks where to put more emphasis. We'll be reviewing things, and I need to know, okay, yeah, this is a topic that maybe needs more emphasis, this needs less, and how we're going to do it. We're going to use a thing called Poll Everywhere. Now, what I want everybody to do now is, if you're using a browser on your telephone or on a computer, you go to pollev.com, and then he asks you what activity you're going into. You go into meir komar 457. You can also do it through a telephone, through SMSs, through texting. You text this message to this number, 052-622-7874. And then every time there's a question, you can text in your message. Sachakol here, it will be A, B, or C. That's all you have to choose, but you'll see it. So everybody, please go in now to pollev.com. It won't let you go to, well, even SMS. You can't send an SMS there to the person that wrote me. It doesn't let you send out.
Yeah.
It doesn't let you send out SMSs. And you're watching now this lecture through your telephone?
No, in my computer.
In your computer, okay. So you can go here to pollev.com.
Oh, okay.
It's easier to use the pollev and not your telephone. It was just in case somebody, for some reason, doesn't have it, then I did that.
It says that it's waiting for the presentation to begin. Is that correct?
That is not incorrect. Because I'm just waiting for everybody to get in. Ronnie, you okay?
Yeah, no, I just, okay. Thank you.
Okay, good. Is there anybody who's not in yet? Because I don't see the list. It's all anonymous. I chose.
I won't be able to get in right now.
Okay. I chose to do it anonymously, so that's okay. It's like this. I'm going to show you, every slide will be a question, And you have to choose one of three choices. And what's very nice about this is everything is very dynamic, and you could see as a group where we're holding, as a group. And you can see, oh, I'm like this. You can see, oh, maybe I'm by myself. Maybe, I have other people who don't understand this topic. Or, the whole idea is not only for me to get information, also but for you to get information. Let's start. How you doing? Choose A, B, or C.
Since I don't have the other options, if it's okay with you, I'm going to send you the answers privately through the chat.
Okay, that's fine. Yeah, so.
Is this in relation to class or life in general?
No, of course. It would be in relation to life, yeah, but then everybody would be C, so no. In relation to the course, how you doing? How you holding? I wasn't sure what to write in English, okay? I wrote איך אתה מרגיש, or in Hebrew, מה מצב. Okay. I chose to use the emoticons here because it's just easier to understand. You understand what I'm saying. Okay.
Do you mean how you're doing in the course, or how you doing
in the course?
today?
In the course.
All right.
In our course. Okay. Is there anybody that hasn't put in that wants to put in? Obviously, you don't have to. It's all anonymous, by the way. As you can see, it's all anonymous. And it's just seeing what's the matzav. Okay.
How do you see it? You just click on it that submits
Yeah.
it?
You probably can just click on it, or you click on A, B, or C. I don't know. I don't remember how you see it. On your screen, what do you do? What did you do? You clicked on it? On the picture? No, you pressed A, B. You clicked on the A, B, or C, right?
Yeah.
This is a picture.
On the picture, yeah, that's good. And here on the screen here, you could see in general. I mean, if you're splitting your screens, you could see on what I'm presenting through the Zoom, you could see how it's 31% are okay, 54% are neutral, and 15% are saying oy vey. Okay, let's go to the next one.
So are you answering these questions as well?
No. How am I doing in the course? I would hope I'm doing okay with it. No, I should. No, I'm not answering. This is for you guys. It's for me. I want to get the information as well. Okay, Big O. How you doing there? Okay. Good. And how about Theta? Theta.
This is awesome.
Good. Really helps all of us understand where we're holding and where to drill down more. Good. Excellent. Good. Let's see. Next. You're given an algorithm. Here's an algorithm. What's the runtime complexity?
Do you mean the full runtime complexity?
No.
or-
The runtime complexity, not the actual runtime.
Like the big O or the big theta?
Theta, whatever. Not the actual runtime. No, that I wouldn't even think about asking. We don't really need that in this course. Okay. Single linked list. Single linked list on the Jewish problem. No. Good. Stacks. Okay. How about the difference between pop and stack top?
What is stack top?
So you know what to press.
Yep. I guess I'm worth 11% of everyone. No, what I mean is that I know what pop does from the stack top of the stack, but is there like another term, stack top?
No, there's a term stack top and there's a term pop. What's the difference between them?
Isn't it just top?
I wrote stack top deliberately. Our gears is top as well. We talked about that. There's some people write top as well.
Isn't there also peak, or is that something else?
Yeah, I think we did that too.
Peak? I didn't use peak, but there is something called peak. Yeah.
I do not remember learning peak.
Is peak
No.
something else? I thought peak was stacked top.
No. Peak, yeah. Peak.
Like, I'm
Is
just
it-
confused with the terminology, not the
No,
actual.
exactly. No, exactly. Peak, I never used that terminology once. Never used it. You probably read it or saw it somewhere on the internet.
I've seen it, yeah, I've seen it a lot on the internet.
Yeah, on the internet. All right. But we don't use the terminology peak. Okay, let's say that. Gotcha. LIFO.
Oh, I was talking to my dad about this, just explaining some data structures things, and he said that LIFO is also a term in accounting, like within.
Yeah.
That was something I did not know.
Yeah, LIFO is definitely a term in accounting. When you're talking, you use it in, let's say, when you're Malay, inventory control. Stam give you an example that while people are answering, it's cool. Let's say you have a shoe, you're selling shoes, okay? And you bought 100 shoes, pairs of shoes for $10 a pair, okay? And now you bought another, let's say you bought another 200 pairs for $20 a pair. I came into your shop and bought a pair of shoes for $50. How much profit did you make? So a lot
Obviously, it depends. If you
Put that on another slide.
the second one.
So it depends on how you do your inventory control. Do you say it's LIFO or FIFO? But the first pair of shoes that I sell is according to the $10 price or the $20 price that I bought it. How much profit did I make? And then obviously there's a lot of chokhmah here because how much tax will I pay? How much did I profit? Did I make $20 or did I make $30 or something or $40 profit? So there's a lot of inyonim here. How do you control inventory? For example, that's one of the examples in accounting using LIFO. Thank you very much for that. That was a nice pause in what we're doing. Let us continue on LIFO. After LIFO, Q, a Q. Just a few more. We still have things to learn today. Okay. That's a Q. How about binary trees? In general, binary trees. Not specifically BST or something, but just binary trees. Okay, next. BST, a binary search tree.
Is the question on this one just what they are or how to use them, like, and everything about them?
How are you in relation to BST? Are you good mates? You're sort of ambiguous or ambivalent, or whatever it's called, ambivalent, or sumushana? How are you in relation to BSTs? You and BSTs, you know, what's our connection? That's in relation to every topic. Okay, just like three more maybe. AVL. How are we doing with the AVL? Obviously, these are more advanced topics or topics that we've just recently been dealing with, and some of you haven't done the homeworks yet. It's really cool watching how things move all the time.
We had something called AVL sort, right?
Also, that's binary sort. Yeah, we used AVL to be able to sort, but AVL is as a concept, AVL tree, and heapify the whole business. Rotations are involved there as well.
So I originally was thinking just rotations, and when I remembered the sort, I downgraded.
Okay.
Doing ABL is going to be a big part of our review.
It will be part. I can see now. Yes, it will be. This is very important for all of us to see where we should start putting emphasis. Heap. How we do with heaps?
Professor, is it possible that these last two are just because less people did the homework? So
Yeah, definitely. Definitely know how to discount what percentage to discount here, because people haven't got to the homework. They've even reviewed, let's say, class from last week on heaps, because you're not up to it yet, because you still have other things as well. No, that's definitely, I take that into account. That's that's for sure, not worry. And I think the last one coming up is quicksort. Yitzchok, I just thought about it. I could have used my other computer and typed in your answers into the percentage instead of through the chat. Just thought about that now. Come on, never mind.
Well, it's pretty clear which areas I'm having more trouble with.
Okay, let's say that. I can see that. Okay, great. Okay, so all right, excellent. That's it. We have officially finished this business. As let us go back now and learn something. Where are we? Yeah. No, not that one. This one. Okay. Thank you very much. I think it was very, very important. Okay. You can hear me okay, right?
Yeah.
Okay. Okay. Tov. So, hey, don't do that. Okay, let's start making some order now in relation to all our sorting methods. So we've seen a lot of different sorting methods. So far, we've seen together 7 different methods. Bubble sort. Anybody want to remind us what a bubble sort does? How it works? Sorry, what it does, it sorts. How does it do it?
It bubbles the numbers up each time, like switching it. If the second number is larger than the first, then it does that n squared times.
Right.
No,
Okay.
sorry. No, it doesn't. Each time it does it besides for the first one. No, yeah, it does an n squared times.
Right. The actual time in the end will be quadratic. It will be n squared, right? But basically, it takes all the neighbors and goes up and up and up, and does that. Excellent. Yes. Very good. Okay. Fine. Next. Insertion sort. We talked about insertion sort. Let's ask Amitai. Amitai is here today? Yes, Amitai. Do you remember how insertion sort works? Ariel, how about you? How does insertion sort work? Do you remember?
Is the place we're supposed to be inserted in the insert itself?
You're getting there. We start inserting and then we start making room for it. Take one, see where it goes, and if there's no room, you push them. If it's at the end, you put them at the end. Start moving things. Insertion. Okay. And selection sort. What do? We take the smallest number and put it in the beginning. Then start looking for the next smallest number, put it in the second place. And each time less and less. And we're selecting the largest number or the smallest number, depending how you want to do it. But we're selecting it. Okay.
I would like to ask about the insertion sort.
Yeah.
How generally can you implement it within an array? Like you have a full array. Do you start with the first one?
Yeah.
And then compare it to the second? Or like you maybe start?
Basically, you say the first one, it's similar to like how we think about with the heap. We say that our sorted array right now is just the first element. And now, take the second element and insert it into our sorted array. So either we'll keep it in the second place, or we'll swap the 1 and 2, and then after that, basically we have a sorted array of size 2. And now you take the third one, and you start looking from the beginning, where does it belong? Is it before the first one? If it's before the first one, just move everybody. If it's the second one, just move the second one. And if it's in the end, leave it where it is. Okay?
Okay, yeah.
Good. What's common to all 3 of these? Besides that they sort numbers.
N squared?
Yeah, they're all n squared. The time for them are n squared. Excellent. Okay. Merge sort. Merge sort Remember what that does? Basically, it says take your array, divide it in two, sort the left-hand side, sort the right-hand side, and then just do a merge, nice linear merge that we know how it works. What does it mean to sort each side? Do that recursively. Do a merge sort on the left-hand side, do a merge sort on the right-hand side, and then merge together. And we do that as a recursive function. That was merge sort. Then we saw quick sort. Quick sort was very cool. Problematic sometimes because you take this pivot value. That's the problem. How do you choose your pivot value? And you take, let's say they take the last value in the array, and you say you're the pivot, and then you put it where it belongs, and you basically what happens is you're going to put it where it belongs, and all the numbers to its left are smaller, and all the numbers to the right are bigger. And then what I have to do now recursively is sort the left-hand side and sort the right-hand side. Again, recursively. And the whole big deal there was, how do you choose the pivot? You take the last one, you take the first one, you take a random value, and quicksort is very useful, we'll be talking about that a bit more.
Are you able to just give that explanation for quicksort quickly again?
Quicksort basically says take a value, and let's say the last value in the array, and then basically what it does, it puts it where it should be in the array.
How does it figure out where it should be, though?
That's the whole algorithm. I'm just explaining in general terms. That's in the end result, that's what will happen. It will be put in its place. In the end result, it will be put in its place where all the numbers to its left are smaller and all the numbers to the right are bigger. That's what the algorithm does, right? I'm not saying how it does it, it's just saying what it does. Okay? Yeah?
Yeah.
Merge sort, as in merge sort, which is doing then what? Can you kind of contrast them?
Contrast between merge and quick?
Yeah.
Whereas both of them are recursive functions, the difference between them, there's a few, we'll be talking about them later on, but one of the big differences is that merge sort uses extra memory, and basically it's true, it divides it into two and then basically resorts it. Where quicksort does the same thing also, where it divides it into two, but there's no extra memory involved and no extra that merge function we don't do. We don't need to do that merge. They're similar but quite different, right? They actually do partition or divide the array into two each time, but it's not. But in merge sort, one difference I would say is merge sort always divides it into two equal parts, plus minus one. Quicksort, we saw that if you choose a bad pivot value, right, you have that pivot value, it could be that only to the left are two values and you have 100 to the right, right? So merge sorts always was splitting into two equal parts. Quicksort, depending on the pivot, we can have problems. But
logically, in a quicksort, you would want to pick the middle value, right?
Yeah, but how do you know what the middle value is? But you're going to start each time going through it looking for the middle value? Then you just increase the complexity tremendously. So therefore, okay, again, we're not talking now, we're not going through and revising all these sorting methods itself. That we will be talking about quicksort again specifically, but in general, that's how it works. That's what's important for us now.
So it's quick because it's quicker than like relative to merge sort? In other words, how does that sum up the sort?
Why does it call it quick? Because maybe it's quicker than the other three on the right. Okay.
Similarities. One is recursive, and for these two specifically, it's also their best case of n log n.
Yeah. Or quick sort. Quick sort. The worst case is n squared.
Right, worst case. But I'm saying maybe average case. I'm not sure what average.
Average case here. Right. Most cases, especially in quicksort, when you use it, it's going to be n log n. But 1 minute, we'll get to that topic. I just want to finish remembering what the four are. A binary sort is using a AVL, where you take the values and you build an AVL tree, which is a BST, a binary search tree. And because I built a binary search tree, if I go through that tree in order, I have all the values orderly. You might see sometimes the terminology tree sort, and not binary sort, tree sort. Again, all these names, when we talk about the new ones, the other ones, there are different names because there is a binary insertion sort, which is a different algorithm. So some people call it a tree sort, binary sort. In this course, we're using the terminology binary sort. Using a AVL tree.
Yeah, using an AVL tree, that guarantees us that worst case scenario will be n log n?
Yes.
For
Because it's a balanced tree.
the exam, do we need to know the implementation of these sorts?
We should be, when we get to the exam, we'll talk about that, okay? When we talk next week, we'll be talking about that exactly, okay? Because I'll also tell you what you'll be given in your formula sheet, okay? Quicksort, for example, is on the formula sheet. Yes. Okay. And the last one was Heapsort, where we're using a heap to sort the numbers. And the whole idea is, if I have a heap and the max heap and the largest number in the heap sits in A1, I could take that and put it at the end of the array, reduce the size of the heap, and then do a heapify, and then the next highest number is up top, and then move it. It's like a form of selection sort. I'm looking for the biggest number each time to put it in its place. The way that I'm selecting it is using a heap, and it's quicker because I just do a heapify, and that's what happens. So these four give me two things that are common with them. Two things that are common to them.
When they all use recursion?
Yes, they all use recursion. Where does Heapsort use the recursion? It's sort of there. It's hidden because the heapify calls itself because it could be that it needs to call itself more than once because it takes the value, puts it up top, and then starts bringing it down. So there is a recursive aspect. All four of these are recursive, and they are all n log n. They're all n log n. Okay. Lovely. Now, what's coming to all seven of them?
They all sort things.
They all sort, yes, that's very good. They all have sort in their name also, yes.
They all take longer than n.
What?
They all take longer than n.
They all take longer than n. That is not incorrect. That is very good. That's correct.
I don't think it's possible to sort something in n, just like logically, because how could you know what you're sorting if you need to see everything before you can sort it?
Excellent, Ellie. Excellent, excellent.
Just looking at everything.
Excellent. So basically what we're saying is here, these all can't be better than the minimum time that I can run it in is n log n. But there's no way in the world that I can make a sorting method which will run in linear time. That's true according to the Havamina. Obviously, you remember what the main topic of today's class is. It's called linear sorting. And we'll be seeing, yes, there are in certain cases, very particular cases, where it is linear, the sorting method. But we'll be talking about that after this following introduction. All of these sorting methods are called comparison sorts. But they're based on comparisons. All of them compare all the values to each other, or some type of they're doing some type of comparison one against the other to be able to get the solution that we want to have them sorted. That's what we have here. All based on comparisons. And there's a concept called comparison sorts. But one of the things that you can say is the sort a comparison based? If it's comparison based, we're going to prove in a minute that you can't do better than n log n. You can't do better than that in the worst case. But I'm going to prove that in a minute. Let's take a look. To be able to understand what we're talking about, I just want to talk about permutations. Some of you might know that if you learned a bit of probability or the idea of permutations. I have an array with n values, and just for simplicity, we'll say there's no duplicates because we don't want to start dealing with greater than or equal to or less than equal to. Let's just say right now there's no duplicates. How many different ways can I order these elements?
N factorial or n minus 1 factorial, something along those lines.
Excellent. You're right. It's going to be n factorial, and we'll see why. Let's take an example. If n is equal to 3, those are the 6 ways that I can organize the numbers. A1 is less than A2, then A3, or A1 is the smallest, but A2 and A3 could be different. These are the 6 different ways. But let's look at it in a more general term. I want to find the smallest number. There's n possibilities. Let's say in our example, there's 3 possibilities. It could be either A1, either A2, or A3. After I chose the smallest one, I want the next biggest number after the smallest. So who's that? That's going to take me, I can choose from n minus 1 possibilities. There's 3 that are the smallest. Okay, and I chose the smallest. Now, who's left? 2 of them. Let's say A1 was the smallest. So who am I left with? A2 or A3. So I have to choose between the 2 of them. So that's n minus 1. And afterwards, for the last number, in our case here, with n equal to 3, there's no choice. After I chose the smallest and I chose the middle, the highest is what's left. In general, so we have n. First time I have n choices. Second time I have n minus 1 choices. N minus 2 choices, all the way to the last one times 1. And this is exactly what was said. It is n factorial possibilities. That means if I have 3 numbers and I want to find the solution, I have to go through n factorial possibilities to find the real one. Okay, that is about permutations. One other thing we want to talk about is a decision tree. A decision tree is a type of tree which is very interesting. A decision tree helps us find the correct answer from all the different possibilities. We said there's n factorial possibilities. So how does that help us? So when we're going through the idea, we have no clue in the beginning. But every time I start comparing something, we know more and more. And a lot of times we can get rid of different possibilities because it's not shaykh already. It's not shaykh. And I'm going to visualize that in a minute. So we're going to use what's called a decision tree to show this process. Now let's see how it works. We're going to have, like in a tree, we have internal nodes and we have leaves. Every internal node is basically a question. It's the comparison. What are we checking? We're going to check between 2 different values. Every leaf, if I'm in a leaf, that's one of our n factorial permutations. Let's straight away look at it. Here's a decision tree for our 3. What we just did now with 3. I'll compare A to B. That's what I'm going to do in the beginning. I'll compare it to A to B. Now, what's great about it, when we're using a binary tree like this, it's either yes or I don't know. So let's say A is less than B. So then I'll ask a question. Is A less than C? And then if it is, then what do I know?
A is first.
I know that A is the smallest, that's true. But I have no clue in relation to B and C. I have to still ask another question. Who's bigger, B or C? If B is less than C, then what? This is the answer. In green, you see the leaves, and in blue, you see all the internal nodes. So we know that A is less than B, which is less than C. That can? Yeah. And if B is greater than C, then we know that the answer is ACB. Again, the leaf is the actual possibility. Internal nodes is always questions. Now A here, oh, sorry. If A here in relation to C, what happens with AC here? What's going to happen here? What do I have to do?
If A is greater than C, then C is first, and then goes CAB.
Excellent.
Well, not necessarily.
Yes, yes, necessarily. Let me explain. Very necessarily. Here, I don't have to ask any more questions. I know that A is less than B, but I know that A is greater than C. So obviously C is going to be less than B. I don't have to ask a superfluous question. This is an example where I don't have to ask any superfluous questions. This type of decision tree reduces some of the numbers of questions I have to ask, because A is less than B, Yofi, but A is greater than C. So therefore, it will be C, A, B. Gotcha? Okay?
Yeah.
Yes? Good.
A decision tree is kind of just like a flow chart.
Yes, to a certain extent, you can look at it as a flow chart. And these are definitely all the possibilities. Therefore, once I checked A is less than B, all these possibilities, I don't even have to check. I don't have to look at them. Correct? I don't have to look at all these. These are not shaykh. And again, this way of looking at it is very nice. But again, we see that we have n factorial leaves. There are n factorial possibilities. Now, how I can reduce the number of questions, the comparisons, and that's what the different algorithms do, is how do I reduce the number of questions? So a bubble sort, we said, is like n squared, right? Because it's always going to check each one against each other n times. Now, of course, it's n minus, every time it's n minus I, but in general terms, it will be n squared. But each one has its own nuances, whatever the word is in English. But definitely what we have here is we can look, okay, those are different possibilities. And we basically want to find our paths. We want to find our paths in the most efficient manner. Okay, so now let us start drilling down a bit. What's the depth of a decision tree? The depth. The depth is the height. I want to claim that it's omega of n log n. Omega, I mean, it's the, what's omega mean? The lower bound. The lower bound. I mean, it's lower bounded by n log n, meaning that it can never be better than n log n. It can never be better, the depth. I mean, that's the minimum. It could be worse, but n log n. Why? We know that there are n factorial leaves. Okay, that we know in a decision tree. A tree of height h, I have a tree, the height is h. Then we've already learned that the number of nodes is 2 to the power of h plus 1 minus 1. I didn't even add the minus 1 here because that's just pushed. Okay, that we know from heights of trees, that if I build a tree, the maximum, if it's totally full, complete, all the way to the end, it will be 2 to the power of h plus 1 minus 1. Therefore, we do know that 2 to the power of h plus 1 is greater than or equal to n factorial, because these are the leaves. These are leaves. N factorial, the number of leaves. And this is the whole amount of nodes. So we definitely know that 2 to the power of h plus 1 is greater than or equal to n factorial. Now, let me just do small mathematics. I'll just take the log of both sides. So this is h plus 1, and this is the log of n factorial. What's the log of n factorial? What's n factorial? That's 1 times 2 times 3 times n. Right? That's, I just opened up the n factorial so you see it. For those that remember when you learned logarithms, a log of a product like that is equal to this is equal to the log of 1 plus the log of 2 plus the log of 3 plus the log of n. Right? From here to here, it's just that's logarithmic. Blah blah. So, what is that? We have a series here. Without going too deep, let's go back here. H plus 1 is greater than n divided by 2 times log n divided by 2. I did this by summing up the series. You don't even have to know how I did it. You can figure it out yourselves. Of course, you can also know, but it's not higher mathematics. N divided by 2, that's n. And log of n divided by 2 is n. So basically, I know that the height belongs to n log n. It belongs to this thing called n log n. It's not going to be better than n log n because that's the minimum amount that I can get to. I can't get a height bigger than n log n. Smaller than n log n. Smaller. And bigger for sure I can, but the height is n log n. So if I know that, how's that going to help me? So why did we use the binary tree? Because every comparison has two possibilities. Nachon. You don't have any repeated values. What's that mean? Down in the leaves, we have the unique possibilities. All the unique possibilities are there. Mamash, every one. All the different permutations are there in the leaves. We also have no superfluous questions. When I'm going through this tree, I will never ask the same question twice. I might have a question, is B bigger than C? But it can be two different branches. But when I'm going to go through and look for the correct possibility, I'm never going to ask the same question twice. For example, what we did before, we didn't have to ask with the C, A, and the B, because we knew already that the C was smaller. I didn't have to check the A and the C, or the B and the C, because we already knew the information. There's no superfluous questions, which is great.
We have a question, quick question.
Sure.
I thought for bubble sort and insertion sort that there was an optimization that we could make the algorithm linear.
No. Bubble sort, you can make it linear. Oh, you can make it maybe linear in the best case. No, I feel not. Insertion sort, specifically insertion sort, in the best case, is linear, in the best case.
So how does that fit in with what you just tried to prove?
Because I'm talking about the worst case.
Okay.
Okay, that's exactly what I'm getting to now. All this is leading into this. So basically what's happening is that we need a huge tree. 5 factorial is 120. 6 to 720. 120 times 6, yeah. 120. 720. That's just with 6 values. It's a huge, humongous, I don't know what the word is, humongous, something like that. Huge curve. The trees are not tangible. They're huge trees. This decision tree to be able to find. It's really big. But we have to go through because we can compare accordingly. So, look at the sentence. There cannot be an algorithm in the worst case. Again, I'm talking about the worst case, not the best case. In the worst case, it's very funny English like this. saying in the worst case, the best time is, its best time is n log n. That's the height of the tree. But I can never make an algorithm which is based on comparisons that its runtime will be less than n log n, or it will be better than n log n. What's better than n log n? Less than. I can't, because this is basically what we've proved, because we're making these, we're going to have to go through some type of tree. However you're going to do it, you're going to be doing all these comparisons, and we have to get to that leaf. This shita does it a bit with the kvetch here. Oh, and you know what? With the bubble sort, you saw a kvetch where I can optimize it because I can have a flag. I don't know if you saw that in the intro course. I show it in my groups that there's a nice kvetch that I can have a flag if I've done a swap. If I haven't done any swap, once I've gone through everything, that means it's already in order. I don't have to continue. But again, it's still going to be quadratic, right? So, nachon, if I look at the actual runtime, on the average I've saved. But in general, it's still going to be a quadratic runtime. So basically, our takeaway is the following. Anything based on the comparisons, the worst case lower bound is omega over n log n. That's the lower bound of the worst case. Obviously, best case could be n. Best case can be maybe ocean 1, maybe. Best case. If it's sorted already, according to the algorithm, well, it's fine. Okay.
Wait, I don't think it could be, how could it be O of 1? Because you still need to go and see it sorted.
Yeah, that's true. So
even if I give you the best case,
you're correct. It's n. O of 1's not correct. Right. Very good.
Ignoring the sort where you give it an array and it's done.
No, you're right. No,
but if it's in a tree, then the best case could be log of n.
Oh,
no?
Okay, whatever. But again, we're talking about the worst case right now. Okay, if that. Okay, that we understood already. We understand that. We don't have to ask. Okay. Now, one other theorem. Again, I want to look at it from another angle because it's a very important concept of the low order chasam. What do we call it? No, in English, what did we call it?
Bound.
The bound, the lower bound. So, if we look at this whole decision, I'm repeating in a different way to be able to make sure that everybody chaps what we're talking about. So we know the following. We know that every single path in that tree, from the root to any leaf, is a possible solution. That we know. Every single path in the tree is a solution. That's one. We also know that the length of the path, which is also the height, is the number of comparisons. It's not the height of the whole tree, but the length is the number of comparisons. What else do I know? I also know something else. The height of the tree is the longest path. In the worst case path length. What's that mean? The height of the tree. What's the height of the tree? The height of the tree is said is the longest possible path. In any tree, a binary tree. What's the height? Height means give me the longest path possible. The longest possible path is our worst case. The height of the tree is our worst case scenario. Like in the example I gave beforehand, right? So, we can also solve it after two comparisons. The height of the tree there was 3. And that gave us also the worst case. There is cases that you can do it in 2. But we know 3 things. We have all the different paths. We know the number of comparisons is the length. And the height of the overall tree is the longest path. Therefore, what do we know? We know that the height of the tree is omega of n log n. So therefore, the number of comparisons that I need to do is omega of n log n, because we said that the length of the path is the number of comparisons. And if we know that the height of the tree is n log n, which we talked about beforehand, therefore the sort needs n log n comparisons.
Professor,
Yeah,
I'm a little confused. The length of the path is the number of comparisons.
right.
And oh, so it's n omega of n log n because we have to sort n things, and each one is log of n comparisons. Meaning each one has to have a path from the going again from the root to the leaf.
Yep.
Okay.
Good. Excellent. Okay. So therefore, that we saw. Now, two small things before we take a break. Yes, we have just enough time. Okay, like this. Two things that we talked
Wait,
about.
sorry, I have one more question going back. Sorry to interrupt.
Yeah, Ellie.
The number of total nodes, including questions in our decision tree, is n factorial, correct?
No. Question of the questions?
Yeah.
No, the number of questions is not n factorial. The number of possible solutions is n factorial.
Number of possible solutions. So what's the number
Indeed. Of comparisons?
Yeah.
That's going to be very dependent on the algorithm that you're doing. I could talk about, in the worst case, the number of comparisons would be 2 to the power of h plus 1 minus n factorial. I never even thought about it.
Okay, so never mind. I was thinking of something, but I don't think it's relevant, so it's okay.
Fine. Okay. Two small things that we've talked about, just derech agav, just incidentally, and I said later on we'll talk about it a bit more formally, and now's the time. The first topic is called a stable sort, but I can take any sort method and I can call it, is it stable or not stable? What's it mean by stable? Let's take a look at this example. Here's an array. This is before, and this looks like what it's after. Okay, I sorted it. Makes no difference which system you use, which algorithm, it's sorted. Now, take a look. I have two values here, two keys which have 18. All right? A sorting method, which we call stable, we call it stable if the order of those elements are kept. For example, I colored now the 18 is 18 green, 18 purple. If after the sorting the array looks like this, then we'll call it stable, meaning the relative order between them. Now, this is very important a lot of times when you're doing some type of sort and subsorting. I don't want Moshe Cohen to become before David Cohen Pitom, right? It could be that I have more elements involved or whatever. But a lot of times, in a lot of applications, algorithms, we want to keep, if it's a duplicate value of a key, keep it in the same order that it originally is. Now, again, we're adding now another factor in choosing your sort method. You're building an algorithm. So you know that you have to think about time complexity. You have to think about space complexity. Another issue now that you have to think about is it stable or not, depending on my algorithm. If after the sort, the 18 becomes like that, then it's not stable. It's not stable at all. Okay.
In what kind of algorithm would that happen, though?
Oh, what a good question. Bubble sort, is it stable or not?
Yes.
Yes, because we're doing that, it's no problem. Insertion sort, it's also, because we're inserting it, so whatever number is getting inserted, it's after, that's not a problem. Selection sort is not. Because what selection sort said, okay, start from the beginning, find the biggest number, the smallest number, and swap it with A1. Now that value in A1 might be a duplicate value of something later on. And I'm going to put it now after the previous, the one that I took away now. So definitely a selection sort is not stable because of the algorithm, how it works. Okay, it's not stable, it's not stable. Sometimes it could say in Hebrew, loch patli. Well, what's the difference? But if it is important to me, I can't use selection sort. Another one is called merge sort. Is it stable?
Yes.
Not necessarily.
Yes. Why? Why not?
Actually, no, never mind. Yeah, I guess it would be.
It is. It is. Quick sort. Is it stable?
Yes.
Pshita shebe, pshita should not. Why? What was the quick sort? How did it work with that partition algorithm? So I have my pivot, and then I start moving everything to the left and to the right. And things get mixed up there totally, because all I know is that to the left is all the numbers small. It doesn't keep the relative order between them. Quick sort is definitely not stable. Binary sort?
Is not.
I have a 50% chance if I just say like, yeah, sure.
Okay, so it's yes and no. Why yes and no? And now I'll remind you what we talked about BSTs. If you remember, I made a very special distinction that we said left is less than, and to the right is greater than or equal to. If I take the values which are equal to the right, greater than or equal to the right, then it will be stable. Because what happens? I have my 18. Okay, I built my 18. Now another 18 comes. I don't want it on the left-hand side, because then when I do the in order, the second one will come before the first one. But if it's on the right-hand side, bravo. Again, the idea is that if we say that in a BST, we're going on equal values, go to the right, then we're okay. Because then the in order will pick it up after the first time. Nice. And a heap sort, is that stable, a heap sort?
No.
For sure not, because that heapify business, you're taking that last value, putting it up top, and then sending it down to its place. Heap sort is not stable at all.
Okay. Just to be clear, binary sort, in the way we defined it, is stable, but the way others define it, it's not stable?
Yeah, no, but Roiva Oilam is, it's stable. But again, depending how you built your BST. If for some reason you built your BST that to the left is equal, then it won't be stable. Okay.
Why is it important that an algorithm, a sorting algorithm, be stable?
Because in a lot of applications, you want things to be according to how things, according to the order that they are. Let's take an example. Let's say I am doing some type of sorting, and I sorted according to last name. Coins, right? So I have 2 coins. And now I'm going to sort it again according to the first name. I don't want Moshe Cohen Pitom to become before David Cohen. I want the David Cohen to come before the Moshe Cohen. Am I making sense? As an example? Seems to be a good example.
Mm-hmm.
Okay. Okay. Now, the last thing before we take a break. I'll explain. What's in place? In place is very simple. In place means that I'm using extra memory. That the algorithm uses extra memory. We have the array A, that's what's given, and you're saying sort array A, bubble sort array A, quick sort array A, quick sort binary sort A, binary sort A. Which one uses extra memory over and above O of 1? O of 1, meaning some type of temporary value, that's okay. Anything above O of 1, okay, let's see. Bubble sort uses extra memory?
No.
No.
Is in place.
It's in place. Insertion sort is in place. Selection sort is in place. Everything's done inside the array. Merge sort.
Oh boy.
It is not in place because how does it do it? It takes each half and copies them to a temporary array, does the sort, and then merges them back in. If you remember, we defined there two additional in the algorithm. Take a look there. We defined two temporary arrays left and right to be able to do the sorting recursively. So definitely merge sort does not. Quick sort is. And with all the games, with everything, with the pivots and everything, and the partitioning, whatever, everything's done inside that array. We don't use extra memory. Binary.
Well, because it just sets the boundaries within the array that it's already
It
in.
moves things inside the array, but it's not build. I'm not using extra data structure. Right? I didn't build any array or anything. I'm using the existing array. Everything's done inside that existing array, just like a bubble sort. A binary sort, is it in place or not?
Yeah, it can be in place.
It's not. No. Hey, I wrote yes, but it should be no. I didn't fix that.
Why? What if you
Rega, I'll explain. Rega, I have to write that down. It's very important. I have to fix it. The binary. It's not. I'll tell you why. There's a machloket. At the beginning, actually, I even told some of my students that it is. But then I looked in the different place scheme, and I'll give you the answer. It's like this. If I'm saying that, okay, I'm inputting numbers. Give me a series of numbers. How does it work, the binary sort? Take the numbers and build a build a AVL tree. Build a VST. Right? That's what we're building. We're building AVL. Now, if the source of my values is, let's say, from input, so I don't have extra memory because I'm building the actual tree now. But if the function is binary sort A, take this array A and please give it to me in order. Sort it, please. So here, my existing array is A, just like in bubble sort and quick sort, but I have to I'm building a new tree. I'm building this BST, so it's extra memory. That's going to be extra memory of theta of n. I'm building extra memory here, and therefore, this should be down and not up.
Is there no way, maybe it'll be a long algorithm, but to simulate what a binary tree looks like?
Yeah, okay.
Yes. An array.
Yeah, but then basically what you'll need is a two-dimensional array or three-dimensional, a two-dimensional array with 3 columns, one for the data and 2 more columns for the indexes. So basically you're adding 2 more one-dimensional arrays. So that's not going to help you. That's how you can simulate, that's how you can simulate a tree. Exactly, I can even tell you prior history, before pointers showed up in languages, the way to make binary trees was using an array, a two-dimensional array. That's how I wrote tree programs when I was young.
Yeah. What is arrays 2 and 3? What are they doing?
They contain the index where the nodes are. Okay, that's just for somebody. Just take it and think about it. That's not what we're dealing with right now. But you can simulate a binary tree using an array.
Good question.
Yeah.
So just like the answer, then you're saying the thumbs up or thumbs down is really, you could say like a yes and no, maybe just how you.
Yeah.
So also, then the runtime complexity really is. Do you need to build AVL or not? Wouldn't that affect the runtime complexity?
No, no. If I'm building a BST, no. Again, we're not talking about the runtime. Yes, yeah. Either way, I have to build it. Either I'm given the array and I build the tree, or I'm inputting it from C-in. Either way, I'm going to build the tree.
Not given the tree?
No, I'm not given the tree. I'm given the values in an array. I have to build, for whole micro, I have to build the tree in the binary sort.
So I understand. So then again, either way, you need extra memory, don't know?
No, I don't have to. No, I don't need extra. No, I'll need extra memory. According to binary sort, I have to build a tree. I need extra memory, yes. Yes, no?
Well, I thought you said there was a way that people were saying you don't.
No, but I'm saying, but it's still extra memory. It's still. I explained to them that it's extra memory in the end result.
It's really a mistake. Everybody would say that it's thumbs down.
Yeah, it's thumbs down. Right. And now Heapsort. Heapsort is definitely in place because everything's done in that array. We're playing around when we're sorting it. That whole business with the max and the max heapifying everything. Everything's done in an array of the heap. So definitely it's in place. Okay, this is a concept, in place versus, not versus, and stable. And when we look at a sorting method, we can say, is it in place or is it stable? Okay, we're gonna take a break now. I definitely need a break. It is now, started late, you know what, we're perfectly on time according to what I had planned, because we started like 10 minutes late, and yeah, good. So we're going to continue now in 15 minutes, let's say 13 minutes. 6:30, okay, 12, 13 minutes, would be 6:25, 4:25. How about 4:25, we're meeting again, okay? So let us take a break. Let's take a break. Thank you. I'm pausing the record. Okay, so let's go back to what we were dealing with. And we shall share the screen. And here we are. Oh, looky. Binary sort is thumbs down. Great.
How did that happen?
What? How did that happen? Clarify, something happened. Yes. I'll update the file on the website also after class. I'm sure there'll be more mistakes as well, so I might as well fix them all. I just loaded up once.
Is it possible to quickly explain why binary sort might need outside memory?
Who? Which one?
Binary sort.
Binary sort needs extra memory because we're building a binary tree. We're building a BST.
Oh, so when you say binary sort, you do not mean the classic sense, so you with an array.
What's a classic sort of? No, different. Rega, because David, you're making a classic mistake. Differentiate between search and sort. When you said classic, you probably were talking about binary search. Yeah?
Yes.
The search and the sort, two different concepts. Okay? Good. So now we're going to start talking about linear sorts. Today we'll be seeing two different methodologies, how to sort variables in linear time. Linear, yes, linear. Okay, so we're going to see two different ways. Now the first one is called a counting sort. Counting, not accounting, but counting sort. Now, I'm going to show it to you. All three ones, I'm going to talk about what's the key description, how much extra memory, is it in place and stable, because these are things that we know about. One thing we do know, that its complexity will be n, but we have to prove that as well. Now, the whole idea of a linear sorting method is, first of all, it's not based on comparisons, because we already proved that to be a comparison can't be linear. So it's going to have to be different. Now, the thing is that the three different types of sorting methods that we'll see now are, it depends on the key. It won't work for every key. It will only work for certain keys. Keys, again, that's the value that we're sorting according to. A counting sort works like this. The key has to be a number, a whole number, an integer, between 0 and k, including 0 and including k. That's what it has to be. It won't work if it's a what you call it, a shiver, a decimal number. If it's a string, it won't work. It has to be a whole number. It can be negative. it uses additional memory. It uses two arrays. One utility array, the size of k. Now, I just want to remind you what this notation, you see this O dot dot k? A reminder, this tells you what the indexes are. Usually we said in our course, we're going to always start our arrays from 1. But here I'm saying, I'm just informing everybody, whoever's using this, that the array C starts from 0 and goes all the way up to k. And we're going to put our final answer into B. The original array is A, count sort A, and hocus pocus, after I did the function, in B, I'll have my answer. I'm telling you now already that obviously it's not in place. That's because look, we're using all this extra memory, and it is stable. It is stable, and we'll see why it's stable, how it's stable. Okay, so that's just an overview to understand what we're talking about. So let's straight away look at an example and understand how it works. It's like this. This is the whole algorithm. Wow, it looks complicated. Look at all these loops. How can all these loops in the end become n? Let's take a look. So let's take stage after stage. Here is my array. I want at the end that in B, it will go 0, 0, 1, 1, whatever it might be. So the first stage is, I'm going to initialize my counters. Again, one thing I have to just say, that the range of our numbers here are between 0 and 6. As I can see here, that the numbers that I have in my keys are somewhere between 0 and 6. Okay, if that's the case. The first stage is a loop. Very simple loop. I is equal to 0 to k, ci is equal to 0. Lovely, just introduction to computers. What's the complexity of that loop?
N.
Somebody else want to say something else?
Hey.
What? What's the complexity of this loop?
What is K6?
We don't talk numbers. We don't talk numbers. That's a constant. We don't say C6.
It's O of 1.
O of 1.
It's O of 1 because I could increase k.
Yeah. It's not O of 1.
It's k.
It's k. But we're so used to always saying n. Be careful. When we say we have a loop, it's depending on the length of the input data. Here, k is the number, but actually it's not even, it's theta of k. It's dependent on k. Lower and upper, it's theta. It's not better than k, and it's not worse than k. It's k.
It's really k plus 1 then, since we're starting at 0.
Yeah, but k plus 1 is k. And when we're talking about orders of magnitude, when we're talking about theta, the plus 1 just goes, we don't see him. He's gone. Okay, that was the first stage. That was easy. Second stage says like this. We want to count the frequencies. The name of the sort is count sort. So obviously we're going to have to do something with counting. So how does it work? This is the loop. Yo. Interesting. Loop. J is equal to 1 to n. C-A-I-J. What are they doing here? Something we learned in Introduction to Computers. You learned about an array of counters. AX is equal to AX plus plus 1. What's that mean? That you take your X and the index, you want to, at that place, add 1. So here, I want to add 1 to who? C. And what's the place? AJ. 6. A6.
This is equivalent to like C++ plus equals or like
Yeah.
like I++ or like any of that syntax.
Yeah, but this is just written fuller. Actually, it's easier. So basically, what are we saying? J is equal to 1, J is equal to 6. So in C6, right, AJ, AJ is 6. In C6, add 1. So it was 0, add 1.
So we're counting how many instances of each number there are?
Sorry?
So we're counting how many.
So basically, after we go through the whole loop, we know in C, in each index, we know how many zeros are, how many 2s, how many 4s, 5s, nebich. There are no 5s here. So the value of C5 is 0. We're counting how many numbers of each one we have. Count sort. Now, how does it help me? How does it help me?
So now we could just copy each C times the value of the place it's in.
So basically what you're saying, go through this loop, right here, 0, 0, 1, 1.
Yeah.
It's a double loop. All right, it's a double loop because I'm gonna have to go through all these K values, and then I'm gonna have to go through whatever here is the CI. I have a loop, internal loop according to CI.
Yeah, but you have a guarantee that the sum of all of those numbers in C
is
N.
N.
So it's not going to be N squared. It's just like that loop is just N.
Just N times K. Worst case will be N times K. Like they're all 6s, or except for 1 maybe. So you're gonna have N times K.
Isn't N times K still linear?
Okay.
No.
Again, it depends what the K is, what the N is. Okay, good. You guys are really thinking. That's great. Let's continue and understand what we're doing.
To do this.
You'll understand. You'll understand in a minute why your discussion right now was excellent, and you're really starting to feel a bit how this is working. Let's just see the whole thing. The next stage is another loop. We're going to compute the cumulative frequency of each one. Again, go through the whole K elements in the array C, and we're going to say that Ci is equal to C plus Ci minus 1. So in C, now we're starting from 1, right? Just remember here, we had 2, 2, 2, 2, 2. So now C1 is equal to C1, I is 1, is equal to C1, that was 2, plus, how many I had beforehand? 2. C2 is equal to 4 plus 2, 8 plus 2, 8 plus 1, there's only 1 4. 9 stays 9 because it's 0. It was 0 plus 9. And here I get 11. Basically, I have a cumulative frequency for each value. I know how many I have, how many 2s or less I have. I know that I have 6 2s or less. I have 11 6s or less, and that's correct because the size of my array here is 11. Right? My size of my n here is 11. Why does it help me?
So now starting from the back of the array, you can place each number at that spot, meaning in the 11th spot, place a 6.
Yeah.
In the 9th spot, place a 5, but then in the 9th spot, place a 4.
Yeah, but what's in the 10th spot?
Then afterward, then you just fill in all the gaps.
No, up until the you go through the numbers, and if the number is between a value I and the value at I plus 1, put it into that. You just put them into their spots.
It gives you the last indice.
Yeah.
It gives you the last index for whatever number it's stored in.
Yep.
So for 6, it tells you where the last 6 is. It's in index 11 of the B array, or where it's going to be put.
Okay, good. You're saying correctly.
And the difference between that and the previous one is how many you have in each index or whatever.
So basically what you're telling me, which is correct, that now I have in C indexes that I can play with. Now let's take a look. What's the last final stage? And here I added the index numbers in B to understand it. We're going to have a loop for j is equal to n down to 1. We're going to start from the end. We're going to start from the end. Yeah, why did I put that in orange? I fixed that. So what happens here? There you go. Yeah, there you go. Okay. I forgot to erase. I made nicer things for you and I forgot to erase the originals. Okay, so basically it's like this. J is from n down to 1. Look at this command. Wow, this looks really confusing. No, what's it say? Okay, let's take it easy. AJ is 2, correct? This is J. AJ is 2. So put a 2, please, in what's on the left-hand side. What's on the left-hand side? Go to array B.
Wait, J starts by pointing at the end this time?
Yes, J starting from n down to 1. That's the loop. We're going to go down this way. And we'll talk about that in a minute. Why? So what are we doing? The B, put a 2 somewhere here. In which one? B. And look at this. Who is this? Ah, okay. So what's the value of this index? Let's look. Oh, AJ is 2. AJ is 2. The C of 2. Who's C of 2? 6. So basically what it says here is in B6, put a 2. Again, how did I get that? AJ is 2. The C of 2 is 6. So therefore the B of 6 is going to be a 2. Okay, because this is the index, the highest index possible where 2 will sit. It can't sit above 6 because it's the amount of numbers up to, including the 6. You know, that's the index. What's the next command in the loop? The loop has 2 commands. C of AJ is equal to C of AJ minus 1. Who's AJ? C of 2. C of 2 is this one, this guy, 2. Reduce it to 5. Why did we do that? Because what will happen next time we find a 2, later down the road here, and put the 2 here in index 5. Let's do another iteration of the loop. J is now 3. So take AJ, AJ is 3, and put it in B of the C of AJ. Who's AJ? A C3. Who's C3? Where is it? C3, where are you? Oh, here you are, 8. So put in B8 the 3, which is very correct. And we continue going down and down and down until we fill up the whole array. That is count sort. Bravo.
I have a question.
Yeah, shoot.
I feel like it kind of got needlessly complicated in the middle there. I have a hunch as to what your answer to this question is going to be, but I'll just say it anyways. So in our first, after our first, okay, so we counted up all of the elements in our array and we put them into C, right?
Yep, you're right. Good.
Okay, so avoiding the whole complicated step of making C into the sum of all the.
Just put them in. Just copy them over.
We already know there's 2 zeros, so we put B. We put the index into B 2 times, exactly. And then we go to the next one. Why can't we just do that?
We just said that. Yeah, definitely. You're right. Does anybody want to say why we'll be interested in doing what I just did?
Because to make it stable.
Correct.
That's why we started.
if I want it to be stable, then I have to do it this way. Because your way of doing it, it's not stable at all.
It's not stable, but for counting sort, it's a very specific sorting algorithm. It only deals with whole numbers from 0 to k.
Yeah,
so
but
Those could be our
we don't
keys.
really.
Those
Why
could
would
be
we
just
care
like
so
a-
much about it being
okay.
stable?
data structure.
Okay, you guys are
Could be
correct. Let me explain.
Object.
Let me explain. Don't forget, this is a key. It could be this key is part of a whole big object with all the information. It's your Taudat number, some number, right? It's your client number, right? But there's a lot of information with it. I can't just put a 0 there. I want to take the whole kebab. We're talking
Well,
about
but if you're sorting by Taudat, then it doesn't matter what. And you have
no,
the
no.
information.
Obviously, Taudat's not a good example.
A good example, I guess, is if 3 or 4 different people all put in the same numbers and
Right.
and we put them in an order, but they put in the wrong numbers, so they repeated. So you want to have all the numbers be in the right way. You'd want it to be stable for that.
Yeah, actually, what I just said was not correct because we can't talk about a key as part of a the object because I have to copy the object itself. In C, I just have the key number. I don't have the object itself. That's for sure. But what you said is correct. If I want the algorithm to be to be stable, then I have to do it this way because I'm going to load it up from the back. And I'll keep the stability of the numbers with the key. Yeah, definitely. Yeah, definitely keep it.
These are just keys to the same object.
No,
like
they're not keys to the same object. They're keys.
No, these are the same keys to different objects.
Yeah.
A few that are 8, and they might be different objects, but if I load in my keys in the right or the wrong order, it won't matter because each one is pointing to a different object. The object is the same key.
Mm-hmm.
So I don't see how stable really matters here. Like
Okay.
in this scenario that we're talking.
Okay, well, we're talking about now. You're correct. I'll try to build an example to show why the stability. Again, you're asking good questions. To bring an actual example, I want to bring examples actually from the shetach. When you're actually using it in the workplace. I'll build a couple of examples for you guys.
Are they correct though that if indeed you're just trying to sort numbers and you want to sort it in linear time, you can do this algorithm and just skip it and even simplify the algorithm and you'll have it in linear time?
Yes, definitely. If I'm not mistaken, if you go to the Visual Algo simulation site, that's how we'll do it. If I'm not mistaken. If I'm not mistaken, that's how it works. Yeah, pretty sure. Okay. So then we reduced that to 7. Okay, fine. And then we finished the whole business. So let's just recap the algorithm as it is. We're going to initialize the array. We're going to do count how many. We'll do the cumulative business. And then in the loop, we're going to put the actual value in its place from n down to 1. And we'll reduce the number of recurrences. That's basically the algorithm, how it works.
How do you find k?
What?
How do you know the range? How do you know the range?
No, that's given to me. Yes. So either the counting sort here has to be a comma k. Yeah, you know what? The actual function. Oh, but actually the n. Where's the n come from? Right. So really, you're saying that I should send 2 parameters, n and k as well. Let's just assume right now they're global variables. Okay, n and k. But very correct, Pinchas.
This is not recursive whatsoever, right?
No, not at all. Very iterative. A lot of loops. But the 3 ways that we look now are basically iterative. One of them you can do epis a bit recursive if you really feel like it, but you don't have to. Okay, so let's take a look at the analysis of this.
Wait, so how does this go against the binary tree that we
Okay,
created?
let's take a look. We already said that to initialize the array, it's theta of k. Everybody agrees with that? Okay. The next loop, what's it cost me?
N.
N, theta of n. Not better and not worse than n. That's theta, not better, not worse. What's the third loop?
K.
How much?
It's theta of K.
Of k, theta of k. Again, another loop of k, 1 to k. 0 to k, 1 to k. No difference. The loop, j n down to 1. How many times is that going to happen?
N.
N. And what am I doing in the loop? Two commands which were constant, O of 1. Both these commands are O of 1. Yeah? Both these commands are O of 1. So therefore, this loop is going to cost me theta of n. Sorry.
I mean, really, it's 2n, but that just becomes n, right?
Yeah, it's n. Okay, so what is the actual run? What is the runtime here? We have twice theta of k and twice theta of n. I mean, the actual thing is the actual complexity of theta k plus theta n plus theta k plus theta n. I have two theta k's and two theta n's. So that means I get rid of the 2. So basically, that is the complexity, theta of n plus k. Linear. Now I'm going back to your discussion beforehand. Is that linear or not linear? It's n plus k. Okay, say that. But watch this.
K is maximum n, so it's maximum 2n, which is just n.
Okay, you're saying k is maximum n. How did you get to that?
Because k is the number of different elements that we have in n.
K is the range of the numbers, not how many.
Ah, the range.
So that could be very high.
Ah, so if I have a set of 2 numbers, but the first one is 0 and the next one is 1,000,000, then
right. Now, see, the whole idea here is when, again, we're saying, look, you just learned a new sorting method. When is it appropriate to use? So basically what you just said now, if my range of numbers is larger than the amount of numbers that I actually want to sort, then this is going to be boom, not going to be Kadai. Okay? So if we're assuming that our K is no bigger than the N, it's even less. I mean, the top number will be N, but usually it will be smaller even. I mean, counting sort works beautifully for a small yachasit, I mean, a relatively small number of values with a large N. If I have
It's not a small amount of numbers, just like a small range.
The range, I said the range. If the range is
okay, fine.
The range compared to the number of values, that ratio, right? Let's say, you know what, let's take marks, like in Israel, a lot of times you give marks between 1 and 10, not between 1 and 100, right? Between 1 and 10. And I have 1,000 students. That's fine. The K is very small compared to the N. Okay, so if we're assuming that K is bounded by the N, then the whole business, the whole kit and caboodle, as they say, is going to cost me theta of N. Nothing more. And therefore, it's linear, theta of N. Nice. Question?
I didn't follow that. It looks to me like n squared at least times k squared.
Okay. Here it's n plus k. Do you agree with me that this is n plus k? The total of all this is n plus k. How did I get to that? I have 2k plus 2n. The 2, we're not interested in, that's a constant, so we're left with n plus k. Theta of n plus theta of k, you can write it as theta of n plus k.
Oh,
Now,
because they're not nested.
no, they're not nested, of course, that's the whole thing. That is the glitch. We have no nested loops here. Each one's with neatzmai.
So this might be one of the quickest sorts.
This will?
This might sometimes be the quickest sort.
Yeah, again, if my keys are appropriate, then a counting sort will be good. Excellent.
Why are we setting k? Why are we assuming k is O of n?
Because if k is larger than n, then we're going to get to n squared. I can't assume that if k is going to be larger than n, then my whole complexity will become n squared. And it won't be.
I don't see how that happens.
Why not?
We just have a bigger array. We just have a bigger B array than the A array.
Yeah, but look at your loops. What are you doing? So basically, you're going to have here is O of n plus n? No. Will it be n squared? For some reason, I think it's going to become n squared up to n. If the k is really large, my tvach is really large, and my n is really large, it will become n times n, because here this will be n, and here this will be n. Intuitively, I see n squared. I have to see why I'm not seeing the n squared. Because theoretically, it's like, okay, look.
Yeah, I think it just uses a lot of space. It won't actually like.
It uses a lot of
It'll
space.
also use a lot of time. If k is 100 times n.
Right, then, yeah. And therefore, you're getting, if you're looking inside, exactly. So if you're looking inside the actual runtime, then we're getting to a much, if we do a proper nituach of the runtime, then we'll get to something much more, it won't be linear. Definitely not linear.
Meaning maybe it's better to say the runtime is k or n, depending on which one's bigger.
The max of them.
Yeah, but you don't want to do that.
That'll still be linear though.
K or n. That's interesting thinking.
Or k plus n.
It is no. It is.
That's what we started with.
It is k plus n.
Right. So maybe they just keep it like that.
Yeah. No. Definitely. Oh, definitely. Sorry. Very, very important. Keep that in mind. That it's n plus k. If we do assume that k is substantially smaller than the n, then you can even write theta of n. But the real answer of count sort is theta of n plus k. Chad mashma'it. It's n plus k. That's very important for later on. It is theta. Sorry?
Up to what range of numbers is this count sort still considered worth it? Like from 0 to, let's say for 0 to 100, is that considered worth it?
It's also a question that n, from what n, I think n is greater than 50 is worth it. Yeah, I remember reading once about it a long time ago. I think I'll look it up as well. You can also, guys, look it up as well.
I'm just trying to figure out where we would use it, because it needs to be a small amount of numbers, a big amount of that numbers. Like, what kind of case do we really have that?
Yeah. Okay. So
like that?
Exactly. That's I already wrote that down to start to find you a couple of good examples for it. That's worthwhile, definitely. So just like I give you guys homework, you guys give me homework. Not a problem. Not a problem.
If I have some like closed set of objects, not necessarily integers 0 through k, can I write a counting sort for my object and just define like instead of 0 to k, you'll make it from the first object, whatever, like the least one to the greatest one, instead of doing it through integers? Like, does that make sense?
Yeah, first of all, it makes sense. Okay, you're talking about a variation, and we'll be seeing with the third one, which is next week, when we get to the bucket sort, you'll see something along the lines of what you're suggesting. And there is a sort, which is a variation of that sort, which is almost exactly what you're talking about. But the whole idea of sorts, how do they make up all these sorts?
Is that it's general? Is that it's like a
You know,
template?
people, get doctorates on sorting methods. But they start doing all these research on sorting methods. In what cases this is better, and that's okay. If the numbers are this way or that way, if they're in reverse order, if they're in the random permutations, and there's a lot of research on optimizing and making the better types of, there's so many different, if you even look for a list of, you can see, okay, a shell sort, that's an important one. That's something that's a nice one. Postman sort, odd even sorts. You wouldn't believe a tremendous amount of sorts. Just throw out a couple of names, right? There's a tremendous amount of sorting methods. Each one with its own kvetch. Some of them are variations of this one. And some of them have different names for the same thing. Different people publish and make suggestions of different sorting methods for different particular cases. And then you decide which ones to use in your appropriate case, or you write your own even. No. Okay. Let's continue. Let's talk about the second one, which is called the radix sort. The word radix in English, are you familiar with that? Radix in English?
No.
The radix is the base. Let's say you talk about number systems, the base. Like base 2, base 10, that you're familiar with from last semester, right? Number systems. You did last semester.
It was digital systems, we call
it.
it.
Marachot Sifratiyot. You did digital systems. So the first topic there was number systems, right? You learned about base 2, base 10, base 16.
Oh, that, yeah.
Yeah, okay. So the base, in proper English, it's called a radix. That's the base. So what's a radix sort? That should have come afterwards. So basically, the key description is the following. This system, this sort will work on keys, which are very particular numbers. They have D digits in base B. So in our terms, in decimal, in base 10, basically we're talking about numbers between 0 and B to the power of D minus 1. Right, so if I have base 10 and I have D digits, I have 5 digits in base 10. So there'll be numbers between 0 and 9,000 and 99,999. Yeah. If I have 5 digits, the highest number in 5 digits is 99999. Okay. That's just to understand it in our terms. But basically, we're looking at D digits in base B. Why this base B? To do everything in base 10. Because we can see that we can use it in nice things. What happens if I have strings of binary numbers? I have some type of application where everything's in binary and in coding when I'm working with encryption, whatever. A lot of different uses stuff for this. So we can talk about in base B in general. It needs extra memory. What? Look at that sentence. Depends which stable sort it. What? This sort calls another sort. See, cheating, huh? It's not a sort. It is a sort. But it calls another sort. So it's in place, yes or no, depending which stable sort. We're going to use, usually, radix sort, very rarely, you'll see otherwise. We're going to use count sort. Why did we do count sort first? Because we're going to use it here. But depending which stable sort I'll use, let's say we'll use count sort.
Use count sort, otherwise it won't be linear.
Yeah, definitely. And also, it's in place if it's stable. No, not because of linear. A stable sort. Very good. Yeah. How much memory, extra memory I use, depending which stable sort I use. I want it to be stable because I want the actual algorithm to be stable, but depending which one I use, does it use extra memory or not? And if we're using count sort, then definitely. We want the count sort because we want it to be linear as well, that's for sure. Okay, so let's take an example. What's the idea? There's a whole animation here that I built to show you the idea, the concept. These are my numbers that I want to sort. And they're all 5 digits, and you know what? And those ones that only were 4 digits, I added a 0. I padded with extra zeros. I don't have to, but just it looks nicer. It's easier to deal with. But okay, these are the ones, the tens, the hundreds, thousands, and the 10,000s. So I have 0 10,000s here. Okay, that's fair enough. Now, how does it work? Watch. Looky, looky. Are we ready? We're going to sort these numbers according to the least significant digit. You'll know about LSBs and MSBs, right? Most significant bit and least significant bit.
Yeah.
Remember those things? Yeah. So now I'm going to talk about LSD. No, not the LSD that you're thinking about, a different LSD. LSD, which is called the least significant digit. LSD. We're going to sort all these numbers according to LSD, according to the least significant. So in the green here, you can see numbers. So just visually, not much visually to understand. So that finishes with a 5, that's with a 9, that's with a 0, that finishes with a 1, that's with a 9, a 5, 2, 1. Those are all my numbers, if you notice. I put them in sort of like buckets like that. And this sorting method, some people call it a sister to the next method, which we call bucket sort or bin sort, but that's not what's important for us. Okay, so I have all these numbers. I'm sorting them. I'm going to sort these numbers according to this digit using counting sort. But this is just counting sort, just so we should know how many, what we have, so we can see it visually. So I could take here, this will be the first one, the second, the third, the fourth, fifth, sixth, seven, all 7 numbers. 8 numbers, no? 1, 2, 3, 4, 5, 6, 7, 8 numbers. And now if you look carefully, they're all sorted according to the last number, the last digit, or the first digit if you want the least significant, and the last digit here. Okay, so it's not sorted yet. What am I going to do now? I took those numbers and put them up here. And now we're going to sort according to the next significant digit. These are the numbers.
This is why it must be stable.
Yeah.
Wait, the numbers on the top there, the first line, that's you took it based on the order that was the result of the previous one?
Here, take a look. 82900. You see this? 05321. And now it's gone up. I just copied. I did a cut and paste. Yeah, from the bottom line to the top line for the next slide. And now we're going to sort it according to this digit. And we get this guy. And if we look carefully, we'll see that all these numbers are sorted already according to the last 2 digits. Yeah. And it's stable. This is very important to be stable, because otherwise we don't want this guy to be over here, because then we're going to have a problem with the order. Okay, now the third one comes. Let's do the same thing. Here it is. And we're sorted according to the third. It's the last 3 digits. And the fourth one, you understood. But anyway, let's do the whole business. I don't want to skip any steps. And we have now our assorted array. Okay? It's sorted. That is Radix Sort. Let's
Wait,
look
you
at that.
the sort is using counting sort?
Yeah, okay, let's take a look, yeah. Let's take a look at the algorithm and then we'll see it. But that was sort of explanation visually, right?
I didn't go by the most significant digit, and then if need be, to have a tiebreaker to sort within.
No, but I want it to be, if you start from the most significant, then you're gonna lose out the order, the afterwards. Because if I start from the most significant, what happens? Then, okay, let's say I have this one and this one, right? And then the next time, this is supposed to be before this one, but now I'm gonna sort it. I can have problems. I can definitely have problems where it will muck up, as they say in English, the order. If I'm starting from the biggest one, because okay, these are okay, but because of the third digit, this is small, this is bigger, then the ones before that will get affected.
Oh, I see.
Okay. There is a variation. Again, variations. There is a radix sort that starts from the most significant digit. It works a bit different, but there are variations differently. But you're not off by saying that, but we're looking at the pshat right now.
A question for this thing. Would it be quicker if we used a different base? Perhaps if we use base 16? Is it then faster or slower? Because we can change bases. We, use base 8, 10, 15. We could use whatever we want.
Lovely. Oh, it's so good listening to you guys. Lovely. Lovely thinking. We'll be talking about that. It's excellent. Excellent.
Can you say that again?
Excellent thought process.
I'm assuming base 16 would be quicker because it takes less amount of times of running through the actual thing. No?
Yeah, because the number of digits will be less.
So let's convert everything to base 200, and then
actually,
doesn't the converting itself take time?
Yeah, exactly. So there is a balance. Okay. Lovely thoughts. You're jumping a couple of steps, and I don't want to lose too many people on the way. If I was in the classroom, I could see everybody. I'm sure I could see by their faces that they're already getting lost with this type of thinking because I didn't understand pshat, and you're already with the drash. We'll get to the drash, not now. Okay. So let's look at the algorithm. The algorithm gets A, and here I did add B and D. I know what is the base and how many digits there are. And the whole algorithm says from I is 1 to D, use a stable sort. Choose whatever stable sort you want to sort A, according to who? Now, I know this is English, the ith digit, right? The ith digit, but from LSD, from the lowest. But when I say the ith, 1 is the LSD, is the least significant digit. This is the algorithm. That's the algorithm, nothing more, nothing less. Basically, the function is a wrapper with a loop calling another sorting method. Right? I have a wrapper here, I have a loop that calls the sorting method. But it's an important loop. Let's just look at it now. Let's look at the analysis of that. So here's our algorithm. And the B is the base, the D is the number of digits, or the length of the key, and N obviously is the number of elements in the array itself, how many numbers we're actually sorting. Each number has D digits, yes. So we're going to use the counting sort as the stable sort. It's just very convenient for us. So now we all know that in base B, there are B digits. In base 10, there are 10 digits, 0 to 9. In base 2, there are 2 digits, 0 to 1. In base 16, there are 16 digits from 0 to F. right? So we have b minus 1 digit, from 0 to b minus 1 digits in base b, b digits. We also know we know the following. If I'm doing a counting sort on n digits, where I know that the n digits are in the range of 0 to b minus 1, that's the amount of digits I have. How much does that cost me, the counting sort? Rega, lama n digits, that's a mistake. That was a mistake in the, was correct, it's d digits. There you go. Doesn't say n, it says d, right? No, n digits, d digits. What's it say, n digits or d digits? What should it be?
It says n.
It says, I know it says n. What should it be? It's n, not d. Explain to me why it's n. It's n, but explain to me why. Not to get, d is the number of digits. But what are we doing here? I got to do this, right? What are we doing here? How many elements do we have in the array?
N.
N. So I'm sorting, just go back to that picture. I don't want to go backwards. Go back to that picture. When I'm taking all the units or the tens, how many of those do I have? N. I have the n numbers, but n digits that I want to sort. I have n digits that I want to sort. That they're part of a whole bigger number. That makes sense. I have n digits I want to sort. I know that the range of those numbers is between 0 and b minus 1. Now, a count sort, remember what we said? What did we say the actual runtime complexity of count sort is? Theta of k plus n, correct?
So wouldn't it technically be better if we had the smallest base possible to keep our k smaller?
Okay, we'll get to that. Again, good talking, but wait. So basically what we're saying now is that count sort is going to cost us k plus n, which in this case it's b plus n. But, somebody? Not but, we haven't finished. What are you missing?
I have to do it d times.
I have to do it d times. I have to do it d times. I'm going to do this stable sort, this count sort, d times, meaning that the whole cost of the algorithm is the theta of d times b plus n. I'm going to do this d times. Sorry, and that is the answer. The actual cost is d times b plus n. Okay, so after that pregnant pause, let me continue. If we assume that b and d to be constants, the base, that's the number. The number of digits. How many digits are you going to have? That's a constant. It's not long strings of thousands of, maybe it is, but it's not now. The base 200, base 10, base 16, base, listen to this. And here I'm giving you a thing to think about. We're going to use, or we're going to use base 27. Why base 27? Why is that good for me? Base 27.
Because it goes up to 26.
Good. And
okay, so 0 to 26. From 0 to 26.
Yeah, good. So why is 26 a nice number for us? Besides Shem Havaya? What else?
Number of letters in the alphabet.
What? It's the number of it's letters in the alphabet. If I want to sort letters, A, B, C, D, E, I have 26 letters. So I can transfer them to be a number. That's very easy. I can take the ASCII value if you want.
If we're sorting Hebrew letters,
So we have ASCII values as well. So you do base, that's already a question, with Sophiot or not Sophiot, right? But it gets a bit more complex. Let's say you don't have finals, so you have 27, so you do base 23. Nice, something to think about. Okay, so that's just throwing out a key. When we do exercises, we'll do at least one together, at least one, where we'll play with that, which it's nice. But let's assume that even if it's 26, or 27, sorry, that's a constant. It's not a function of something else. So if they're constants, then we get, why did I write O here? Should be theta. It will be theta again. Okay. So that's assuming that they are constant. And if they're not constants, then it's going to cost me more. If they're not constants. If we can't assume them to be constants. But again, with the Radix Sort, we're going to try to make sure that B and D are constants. We will see, next week we will be seeing, once we see the next sort, then we're going to start comparing them together a bit. Sorry. Actually, it's very good that we're in Zoom, because if we were normal class time, you probably would have gotten a message that I'm sick, I'm not coming to class today. But I can teach sick from home, so it's good. So that worked out okay. So what are we doing here? We're going to take this, we'll compare it also with the bucket sort, and then we'll start doing all these really things. Okay, what happens if it's not a constant? And, but we can do this. And if we look at this way, again, once we see the whole picture, we'll start doing that next stage. Okay. So let's just sum up right now. We talked about counted sort and a radix sort. Now, he's reminding me to show you a page. Okay, what's the time? How are we doing? Yeah. Okay. It's like this. I prepared a summary of all the sorting methods with a nice table saying what's the name, what's the key, what's the best case, what's the worst case, what's the average case, is it stable, is it in place, and if it's not in place, how much extra memory it takes, and a small description of the algorithm. All 10 of them, all 7, on one side of the page is 7 of the comparisons, and the other 3, which are called counting sorts, you'll see. I'm not going to show you the page right now because we're going to leave it until next week after we see bucket sort. It is on the website, the Hebrew version. It's sitting up in the Machon Lev area. The English version is very similar because most of it's written in English, except for the descriptions of the algorithm, which are written in Hebrew. I'm translating them to English for you. So that's going to be a nice page, which really will help you make order in all these sorting methods. So what did we do today? We talked about sorting methods. We talked about stable and in place. We talked about decision trees. We saw the lower bound being omega of n log n. We started looking at linear sorts, counting, and radix. We did quite a lot of it. Besides looking an overview of the course and seeing where we're holding. So next week, we're going to finish. We're going to do a hadron, have a seal. We're going to finish the actual material, and then we're going to start drilling down into the various topics. And the main way that we'll be doing it is taking previous questions from previous exams and solving them. That way we can understand more fully some of the topics. I'll choose now those questions according to what we did in the beginning of the day today. I saw what topics need more and less. Obviously, not including the linear. We're going to start with we're going to do a lot of exercises just on linear sorts in the beginning next week. And it's the first 2 hours. Then afterwards, we'll start doing some more questions. After we saw what a bucket sort, obviously. So that's what we're going to do. So, I was going to ask you a question. I forgot. I was going to ask you a question from Parshat Shavua. Where is data structures in this week's Parsha? So here you go. Nitunim, hey Mali. That's this week's Parsha. Okay, so Shabbat Shalom. And we'll be seeing talking to each other next week. Kol Tuv. Shabbat Shalom, everybody. Kol Tuv.
Shabbos.
Oh, good Shabbos.
Shabbos.
Now I can see you guys. So now I can.
Where's that now?
Now I can see people. Wow, right at the end.
Really?
Oh, Eddie, that's what you look like. Reagan, where's the baby? Sleeping?
Somewhere else, hopefully.
Wait, where's that now?
I think so, because she's not crying. So
Yes,
it's a binary option.
Yes, very. Okay, great. Okay, Kol Tuv. Bye.